All right, welcome to your very first lesson on flip lessons for basic calculus. So today we are going to talk about limits and how to evaluate limits graphically, because I think the easiest way to start with limits is kind of what they look like. So before you get to what they look like, you really need to understand what the notation looks like. So there are these things called sided limits. And when you have a sided limit, it's when you see this limit as x approaches c, and there's this little plus in the top that you can kind of see right there. So if you want to take the limit as x approaches c and you see that plus thing, what that really means is you are approaching, there you go, you are approaching c from the right. And if you see a little minus up there, that means you are approaching c from the left. And what you need to remember is when you're approaching from the left or from the right, you're staying in the neighborhood of C. So if I'm approaching 4 from the left, I wouldn't start at like 2. I'd start at like 3.7 or 3.9. That's the neighborhood of 4. So a function has a limit as x approaches c if and only if the right and left-hand limit exist at c and are equal. In symbols, that means the limit as x approaches c of f of x equals L, okay, this is just kind of a regular two-sided limit, that is true if and only if the limit from the right equals L and the limit from the left equals L. In other words, if the left and the right limits exist and they're equal, then the two-sided limit exists and equals that value, all right? So let's look down here at this graph. And if you were in pre-calc last year, you probably saw some of this. So it should be a little bit of review and probably pretty easy. So I'm going to go through it relatively quickly here. So if I want to take the limit as x approaches 1 from the right, I'm going to say, okay, here's 1. Here's where the graph is to the right of 1. So I'm going to start slightly to the right of 1 and approach 1 like this. And as I get to 1, the y value is 1. If I approach 1 from the left, here's 1. Here's the graph to the left of 1. As x approaches 1 from the left, y is approaching 0. The limit as x approaches 1 with no plus or minus means I have to look from the left and from the right. So I'm going to use the little magic pen here. So as I go from the left, I end up here. As I come from the right, I end up here. If those are not the same dot, if these values are not the same, then your two-sided limit cannot exist. This limit does not exist. DNE does not exist. Well, if the limit doesn't exist, can the function exist? Is f of 1 existing? Well, that all depends. Is there a point on the graph? At 1, there's a hole here, but there's a point there, so f of 1 is 1. So this row is a great case about how your left limit, your right limit, your two-sided limit, and your function can be very different things. Now let's say, what if I look at 2? So if I come at 2 from the right, so here's 2, coming from the right, I'm going to gently go back to 2, and I get to a y value of 1. If I come at 2 from the left, I also at a y value of 1. As soon as this equals 1 and that equals 1, I know that this two-sided limit is also going to equal 1. I don't even need to look at the graph. Now I can look at the graph and realize that they're both going to 1, but technically I don't even need the graph anymore. F of 2 is, where's the dot? Well, here's 2. The dot is at y equals 2. So f of 2 is 2. And then last but not least, 3, why don't you take a second, and what I do a lot of these videos is I tell you to hit pause. I hit pause on my end, I do it, and then I explain it very quickly afterwards. So I want you to hit pause on the video, do these 4, and then check back and see if you got the same answers I did. Okay, hopefully you did hit pause, and this should have been an easy row. Everything in this row equals 2. Come at 3 from the left, I get 2. Come at 3 from the right, I get 2. There's a dot at 2, and since the left and the right are equal, the two-sided limit also equals 2. All right, so on that graph, we kind of saw some things that looked a little bit like what we see here, so I want to talk about that really quick. There's some similarities and differences between these 3 graphs here, and I want to talk about those similarities and differences in respect to x equals 1. So at x equals 1 here, the function does not exist at 1 because there's a hole there and there's no dot anywhere else. But the limit as x approaches 1 of f of x does exist, and it equals 2. So when the function doesn't exist but the limit does, that means that you absolutely are going to have a hole. In this case, this is very similar to this first one. My function, though, f of 1 does exist and it equals 1. The limit, though, as x approaches 1, just like in the last one, is going to equal 2. And then last but not least here, my function exists and equals 2. My limit exists and equals 2 as well. This brings us to kind of the gradual evolution of what's called continuity. Continuity, in layman's terms, is in a graph, something's continuous if you can draw it without picking up your pencil. If you can draw it without picking up your pencil, it's continuous. Notice, this, I would have to pick up my pencil because I'd have to draw it, draw a hole, pick up my pencil, draw some more. Here I'd have to draw it, draw the hole there, put a dot down there. I'm picking up my pencil all the time. This is not continuous. That is not continuous. But this is just one straight line. I can draw that. I don't have to pick up my pencil. It is continuous. Now, what does that mean mathematically? Well, mathematically, that only happens when the limit and the function equal the same value. So if the limit exists and it equals the function value, then your function is continuous at whatever point that is. Now, what if it's an endpoint? What if there is no two-sided limit? You're at a function like y equals the square root of x, and it looks like this, and it ends right here. Can that be continuous at 0? Yes. If we have endpoints, mathematicians aren't idiots. We like to make things make sense. So if something stops and there's nothing afterward, then we just ignore that side of the limit and make sure that the function equals the other side of the limit, and then it would also be continuous. All right. Graphically, it's continuous if you can draw it without picking up your pencil, and it's continuous if the value of the limit is equal to the value of the function. Now, what kind of continuities are there? Well, there's actually two different kinds of continuities. There are removable discontinuities, and non-removable discontinuities. A removable discontinuity is when there's a hole you can just fill in to make the function continuous. Up here, this thing right here is a removable discontinuity. So is that. Doesn't matter if there's a point outside. If there's a hole, just a hole, and then the graph continues unabated after that, that's removable. However, if it's anything bigger than that, if it's a break in the graph, if it's an asymptote, then it's a non-removable discontinuity. So when the graph is broken and there's a jump or a vertical asymptote. So if I come to this one right here, and I say, all right, for what values is f not continuous? That's going to be any time it's broken. So it's broken right here. It's got a hole right there and no other holes. So where it's broken at x equals 1, there is a non-removable discontinuity. At x equals 2, there's a discontinuity because I'd have to pick up my pencil there, but it's a hole I can just fill in. So at x equals 2, there is a removable discontinuity. Okay? And then last but not least, this is something I know you learned in pre-calc, but you probably forgot it because it's got kind of a unique name. There's something called the intermediate value theorem. In the intermediate value theorem, I will often refer to, and I will just write IVT. So if you see that, that's when I'm talking about the intermediate value theorem. The intermediate value theorem is honestly one of those like common sense theorems that everybody says, why do they have to make it so complicated? The intermediate value theorem says if you go from point A to point B, you hit all the other points in between. That's what it means. But the key here is, now that we're in calculus, the key here is in order for that to work, you have to suppose that f is continuous. The intermediate value theorem only rings true on a continuous function. So if someone tells you f of x is continuous on an interval from a to b, and n is a number between the endpoints, between the y values of the endpoints, then there has to be a number in between where you reach that y value, okay? In other words, if I have a graph and I draw it and I say, here's a function, here's b, here's a, and I say, let's say this is -2, and let's say this is +3. Since f of a is -2 and f of b is +3, that means every y value between -2 and 3 has to exist on this graph. There isn't one that just doesn't exist and fades off into oblivion. They're all there, okay? So, how do we use it? How might you see it in a question? Given that it's so common sense, you kind of want to know how to look out for it. Given that f is continuous on the interval from -infinity to infinity, it's continuous everywhere. If f of 4 is 5 and f of 7 is -7, well, you know what? If I'm going to think about something, I want to draw it. So f of 4 is 5. And f of 7 is, let's say, -7. And it's continuous, so I know it does something like that, okay? Pretend that's still a function. It kind of looks like it went sideways. Pretend this is a decent function here. And I know it goes from there to there. Now, I don't know what it looks like. It could look like that. It could also look like this. It could look like this. It could look like this. It could do a lot of different things. I don't know what it does, but it does something, and it's continuous. So if that's true, and then they tell me that f of x equals 0 has exactly one solution, that means it only crosses the x-axis once. Doesn't that have to happen in here? Can I get from 5 to -7 without crossing the x-axis? No, that's ridiculous. So somewhere between 4 and 7, there has to be a 0. Now, I don't know where, but somewhere between 4 and 7 that has to happen. The only one of those choices that's between 4 and 7 is 5. And then last but not least is a question I made up myself. You're driving along 441 when it had a speed limit of 35 miles an hour, okay, right by Penfield Trophies there. And then further down the road, your speed limit increases to 55 miles an hour. So that's as you're going down the hill and you're heading toward 490. Police officer has a radar gun that determines the speed of each car as it passed the 55-mile-an-hour sign. So he's right there. He's right at the sign. When you pass that sign, the radar determined your speed at the sign to be 55 miles an hour. So the officer pulls you over and gives you a ticket. And you say, but I was going the speed limit. It's 55, and I was going 55. And the officer, who happened to be an old student of mine, said, well, if you have Mrs. Vibber, then you should know exactly why I gave you a ticket. So why do you have one? Well, if you're going 55 miles an hour right at that sign, what were you going right before that sign? Were you probably going 54? And what was the speed limit when you were going 54 before the sign? Wasn't the speed limit 35? Yes, Mrs. Vibber, it was 35, and we're not supposed to speed. You're also always supposed to wear seatbelts. I will remind you of that frequently. Don't speed, wear your seatbelt. This is a don't speed because Mrs. Vibber will get you in jail with math kind of rule. But basically, this is, why do you have a ticket? Because of the intermediate value theorem. Intermediate value theorem says you went from 35 to 55 instantaneously. No, there's no way. You had to be driving higher than 55 miles an hour right before you got to that speed limit sign. There's no other way you could have done that. Not higher, pardon me. You have to be driving faster than 35 miles an hour to get to that 55 speed limit sign. Okay? And then last but not least, two of my favorite comics here. We have the intermediate value chicken. And this one I just like. See, he divided by 0, and then there's a little comic coming. And what you will also learn is at the end of every video, there will be a joke. So I'm going to start with one of my favorite jokes of all time. And this is one of them. My favorite joke is, what color socks does a bear wear? What color socks does a bear wear? You know what? Bears don't wear socks because they have bare feet. I know, it's so funny. All right, I hope you enjoyed this video. I will see you in class.